Hey guys, welcome again to the Maths Club. If you are just joining us, you're welcome. We're happy to have you here. Don't forget to like our videos, subscribe to our channel if you have not, and tell somebody or tell 2 people or tell 10 people about what is happening in this channel. In this video, I'll continue with plane geometry and we're looking at Cyclic theorem. We'll discuss what are chords, the key parts of a circle, and the 6 Cyclic theorems. In the following videos, let's look at examples, and in the next video, let's look at WAEC past questions on Cyclic theorem. So let's get started. Chord. A chord is just a line segment that is connecting 2 points on a circle. So look at this. You see this circle? You see the circle here? You see this line segment? It's connecting this point A and the point B. You connect the points here and the point this. In fact, you also know that the diameter, so diameter which spans across the center of the circle, is also a chord, and that's the longest chord in a circle. Okay, so in a circle, the longest chord is the diameter, so they're just basically stating what I just explained. Key parts of a circle. So look at this. This is a chord, right? You see that this part is bigger than this part. So this smaller part is the minor segment, and this bigger part is the major segment. So all these parts, if I do like this and I do the curve here, right, that is the major segment. And if I do like this and I do the small curve here, this is the minor segment. And because this is the minor segment, this part here is the minor arc, and this part here is the major arc. A straight line that is touching any part of the circle, right, that's passing through it outside, right, it's not passing inside, it's just outside. Can you see it? It's just outside across it. It's called a tangent. It could be slant like this, it could be like this. Just follow my mouse or anything. As far as it's touching one side of the outside or the circumference of the circle, right, and it's a straight line, is a tangent. And of course, all round about it is the circumference. You can see this. We've talked about all these things in prior videos to this. So theorem says that the angle which an arc of a circle subtends at the center of the circle is twice that which it subtends at any point on the remaining part of the circle. So let's see an example. See, look at this guy here. First is that you notice this V, right? This V here, this V, and you also notice this V. Of course, there's an angle between the lines here, and there's an angle between the lines here, right? They're saying that because this is at the center, this angle here will be twice this angle here. Remember, it's the V and it's the V, and they both have an angle in between them. It's saying that the angle at the center, right, the one in between the V that's at the center, will be twice the value of the one in between the V at the circumference. See, one is touching the circumference, one is touching the center. One is touching the circumference, one is touching the center. Same thing too. Look at this V. See this V. See this V. There is an angle between them. There's an angle between them. Remember, one is touching the circumference, one of the V is touching the circumference. Yeah? And one of them is touching the center here. One is touching circumference, one is touching center. The angle between the lines at the center will be twice the value of the one touching the circumference. And we're going to prove it. So don't get it wrong. We're going to prove it. This is the one that does not follow the V and in between, but it's still the same thing. So when you see something like this, see this guy here is touching the circumference, right? This V is touching circumference. The angle here is half of this angle here, and that is the one that is not like this, right? So where you see inside, right? This one is more like inside outside, but it's still the same principle. I'm going to prove why this is so. So let's go to the proof. So the first thing I will do is, let me see. So step 1, you draw a line through A and C to a point P. So let's draw the line here. These proofs are very important because it could be asked in the WAEC question in your theory. Right, so I'll just draw a line here up to the point. So this is the point P. Great. This is the center of the circle. From here to here is the radius, right? From here to here is the radius, right? So second step is I'll label radius CD and radius AC as R. So RR. So what do you know that is showing right now from triangles? These two sides are equal, so that is an isosceles triangle. So I'll just say to form an isosceles triangle, so this guy here is equal to this guy basically. So this R, so I'll remove the. What do we say about isosceles triangle? We said the angle of what? Great. We said the base angles are equal. So the base angle, so if these are, so let me see, in triangle ACD, right, the base angles are equal. So that means this guy is X, this guy also is X. We know that. Great. What else do we know? Can you remember when we were talking about external angle theorem? Right, so said external angle theorem that the external angle is equal to the sum of the opposite interior angles. Remember that? Great. See how all these things they come to play. So we know that from external angle theorem, angle, this is, so look at this, is it's here. So this is the external angle here. This is the external angle here. So that would be angle DCP. Angle DCP is equal to angle this guy here plus this guy here. That would be ADC plus angle let me say DAC. Great. So that would be equal to, this guy here is X, this guy here is X, so that would be X plus X, which is equal to 2X. So angle DCP is 2X. Great. Also too, I will label, see, this guy is a radius, this guy is a radius, so I'll label radius, let's call this BC, and radius, let's call this AC as R. So AC is R, C or BC is also R. So that's also an isosceles triangle. So we know that in triangle ABC, also the base angles are equal. Right, so I mean these are the base angles here and here. So this is Y, let me call this also Y. Great. So from external angle theorem, so I'll just say from EAT, comma, angle, see this is the external angle here, this guy here, this is the external angle here, this one here. So from this point, this line to this point, that is the external angle. So angle, that will be angle BCP is equal to angle, let me call this ABC plus angle BAC, which is equal to Y plus Y, and that will give me 2Y. So that means that this guy here is 2Y. So that means that the sum of the angle here, if here to here is 2x and here to here is 2y, so that means the sum here is 2x plus 2y, and I can bring that out to say this is 2 open brackets x plus y, right? That's the angle at the center, and the angle here, if this is x, this is y, this will give me x plus y. So the angle here is x plus y. So you can say that the angle at the center, right, is twice the angle at the circumference. But this is x plus y, this is 2x plus 2y. Great. So if you are given to prove for this type, it's still the same thing. So to solve this, I also do the same thing. Draw a line through AC to point P. So this AC to a point, let me see, the point P is here. So these are points P. Next thing is label radius CD, this CD and AC as R. So this R and this R. So this radius, of course the base angles are equal. So if this guy is X, this guy also will be X. Great. It now says from external angle theorem, angle DCP is equal to 2x. Of course, so you know that this is the external angle here. So this guy here will be 2x. It now says label radius BC and AC as R. So because BC, this is R, and this is R. So the base angles will be equal. So remember, this is the triangle here. So this guy here is Y, this other guy here, this place here would also be y. Do you get? Because these are the base angles. I know that this one is looking bigger. I just have to make it bigger in terms of the arc, but it's the same thing as this value here. So it now says from E8C, angle BCP is equal to 2y. Of course, we know that already. This is the external angle here. So this entire place is 2y. Great. Now look at this. If this entire space is y and this small part is x, that means that this small part here, right? Look at it. This entire space is y, then this small part here is x. So that means that this space here is going to be what? Y minus x. Same thing too. If this entire space is 2y and this small space is 2x, so that means that this small part here is going to be 2y minus 2x. So I could factor out and say 2 open brackets y minus x. So you can see that the angle at the center, which is this place here, is twice the angle at this circumference, which is this place. So you can see 2 open bracket y minus x, this y minus x. So this basically is for this two. So the same thing applies to this one here. I'll draw a point from A, choose C to a point P. Great. And then I'll label CD as R and AC as R. Great. So if this is the triangle here, the base angles are equal to this x and this is x. We know that already. Great. We are not told that this CP, it will be 2x. Of course, this is external angle theorem. Already know this, so this will be 2x. And we'll label BC as R and AC as R, right? So from external angle theorem, we also know that what angle BCP is going to be. Okay, so when we label this as R, of course, we have to label this is the triangle here. So that means the base angles, this is Y, this is Y, right? So we also know that from external angle theorem, BCP is going to be 2y. 2y, because if you look at the triangle, this is the external angle. If you have any problem with external angle theorem, please go back to one of the videos that we're talking about external angles. I can't remember which, but I think we're talking about triangles in that video. It should be part of this playlist under plane geometry, and watch it, so you understand everything perfectly. So look at this place now. The sum of this guy here, the sum of all this guy here is, let me just draw a big circle here. The sum of this guy here is 2x plus 2y. So if I factor out 2 from it, this will give me x plus y. And the sum of this guy here, if this guy's x gets y, is what? X plus y. So you can see that the angle at the center, right, is twice the angle at the circumference. So this is basically the proof. So any of these triangles that they give you and they tell you to prove, just know what you are doing and you will get your answer. Great. So come again and say the angle which an arc of a circle subtends at the center is twice that which subtends at any point on the remaining part of the circumference. Great. Theorem 2 is called the Thales theorem, and it says that any angle subtended at the circumference by a diameter is a right angle. Let's look at this. So this guy here, see the diameter here. It says any angle subtended at the circumference by a diameter. So you can see the triangle here. Remember, we said the angle at the center is twice the angle at the circumference. See, what is the angle at the center here? Great, 180 degrees, because it's a what? It's a straight line. So the angle at the circumference just be half of it, which will be 180 divided by 2, which is 90 degrees. Great. So it's just an extension of theorem 1. Theorem 3 states that angles in the same segments are equal. These angles in the same segment theorem. So let's see. Can you see this? Just like the theorem 1. See this first one. Can you see the V? See the V here. See the V here. Right. So the angle at the center is twice the angle at the circumference. So this is 2a and this is a. Same thing too. Look at this guy here. Let me just something. And this guy here. Let's say it was something like this. Forgive my drawings. Right. So you can see that the angle at the center, 2a, is twice the angle at the circumference. So these are basically just extensions of theorem 1. That's why you must know theorem 1 very well. So theorem 4 is the opposite angles of a cyclic quadrilateral theorem, and it states that Angle in opposite segments are supplementary, meaning that opposite angles of a cyclic quadrilateral are equal. When we say supplementary, what do we mean? Great, means that it adds up to 180 degrees. So if you don't know that, you know it now. When we say supplementary, it means they add up to 180 degrees. So let's prove it. But before we prove, let's see the diagram what we mean. So the trend tells us that in this case, these are opposite angles. A and C are opposite angles. By the time you sum them up, it will give you 180 degrees, and by the time you sum up B and D, it will also give you 180 degrees. But let's prove it. Don't take my word for it. Let's solve. Let's assume that these are quadrilateral. So I mean, first thing that you want to see is you want to draw a line right across, and you want to draw another line, right? So let me just move this to the edge. Great. So assuming that this point here is the center of the circle, so this point here is point O at the center of the circle, right? And yet here is your R, yet here is your radius, yes here is your radius, yes here is your radius. And it's not up to scale, but take like that. So it forms an isosceles triangle here. Let's say this is A, this is B, this is C, this is D. So it forms an isosceles triangle here, an isosceles triangle here, an isosceles triangle here, and isosceles triangle here. So these two sides are equal, meaning that these two angles will be equal. So if this is A, this side there will be B, this side there will be C, this side there will be D. Great. What do we know from this? I know that the sum of angles in a quadrilateral is 360 degrees. So A plus A, which is 2A, plus B, which is 2B, right? Because I mean, sum of this angle, this angle, this angle, this angle must equal 360 degrees. So I'm just taking one at a time. So this 2A, this 2B, plus this 2C, plus this 2D must equal 360 degrees. Do you agree with me that I've covered all the angles at the four sides? This, and this with this. You can try it and see. You could do A plus D plus D plus C plus C plus B plus B plus A. You see that you still arrive at the same thing. Now I can factor out 2 from this left hand side. That will be 2 open brackets. A plus B plus C plus D is equal to 360, and I can divide both sides by 2. So A plus B plus C plus D is equal to 180. Now that we know this, look at this. I could group it and say, look at, let me take this first guy. This is A, this is D. I could group it and say this is saying A plus D plus B plus C is equal to 180. Do you agree that's possible? Yes, that's possible because you can group, right? This addition. So just say A plus D plus B plus C is equal to 180. And look at C is this is A plus D, this is B plus C, and you can see the opposite of that. So that gives you 180 degrees, right? Great. Also too, this other side, I could have said from here A plus B plus C plus D is equal to 180 degrees. So this is A plus B, this is C plus D, and you can see the opposite of that is equal to 180. So anyway, you put it so that the sum of angles in opposite segments are supplementary. So this is the segment. This one is one segment, this is another segment, right? So sum of angles in opposite segments, this segment 1, this S1, and this segment 2 divided by this line. The sum of angles in opposite segments are supplementary. Now if you look at something, if I have an angle, let's say an angle E here, you agree with me that B plus C plus E should give me 180 degrees, right? Great. So now we said A plus B and C plus D is equal to 180 degrees, right? I could also say B plus C plus E is equal to 180 degrees. Do you agree with me? B plus C plus E is equal to 180 because angles on a straight line. So another alternative way I could describe this and say A plus D is angle at this capital letter A. So I could say angle at A plus B plus C is angle at C. So plus angle at C is equal to 180 degrees, right? Another we could say this is saying A plus B, which is the angle at B, plus C plus D, which is the angle at D. At angle at D is equal to 180 degrees. This is another way of saying this. Great. Look at something. This OB plus C, which is the angle at C, plus this E should give me 180 degrees, because angle in a straight line is equal to 180 degrees, Abi. So I could just say also angle at C, capital letter C, plus small letter E is equal to 180 degrees, right? Is that not it? Great. If I make angle at C with the formula, that would be 180 minus E, and I plug it into this place here. That would be angle at A plus 180 minus E is equal to 180 degrees, right? This degree. So I could say angle at A minus E is equal to 180 minus 180. So angle at A minus E is equal to 0. So angle at A is equal to E. What am I trying to prove? I'm trying to show you that the angle here, which is the angle at A, is equal to this guy here. Is equal to this guy here. I just did a small proof that if the angle at C, which is this guy here, this is the angle at C, plus the angle at E would give you 180 degrees, because angle in straight line is equal to 180 degrees. And I make the angle at C with the formula from it, and I substitute into this place here, and I make A to be the formula after substituting. You see that the angle at A is equal to E, meaning that this external angle here, right, is equal to this guy here. So that's one thing that you need to know. So two things to know from this: the sum of angles in opposite segments are supplementary, and then the angle at this guy here is equal to the angle at this guy. I see questions that these things will come in handy. That's what I'm taking them to explain. And remember, anytime I'm looking at a proof, please know the proof, because these are possible WAEC theory questions. So we've established that A plus C is equal to 180 degrees. B plus D is equal to, you can see that the angle at A, which is green, is equal to the angle at E, which is also green, and we've seen why. Theorem 5 is the tangent radius theorem, and it states that a tangent is perpendicular to the radius at the point of contact. So this is the tangent. Talk about tangent. This is the radius. You can see at this point there is a 90 degrees here. Also too, even if it is bent, as far as there is a tangent, you can always draw a radius to it, and the radius will be perpendicular to the tangent, and that gives you a 90 degrees angle. These things will come in very handy when we start solving questions. So you can see the point of contact, and you can see the tangents. Theorem 6, which is the final theorem, is the alternate segment theorem. One other theorem that you need to know the proof. It says that if a tangent is drawn to a circle, we've looked at what the tangent is, and from the point of contact, right, a chord is drawn. Each angle which this chord makes with the tangent is equal to the angle in the alternate segments. I mean, so much English. But what they're trying to tell us that this guy, this alpha here, will be equal to this beta here. That's basically it. The alpha and beta are alternate angles. So try to make sense of this. Right. So if a tangent is drawn to a circle, see the tangent, and then from the point of contact, a chord is drawn. Can you see the chord PR? Right. Now since each angle which this chord makes with the tangent, this is the angle that it makes, is equal to the angle in the alternate segments. Right. So try to make sense of all of that. There are other ways that people wrote this, right? But we're going to look at the proof of this together. So how do we do that? First things first, that we can connect this guy to this guy, right? This is a radius, and also we can connect this guy to this guy here. This is also a radius. So we talked about tangent radius theorem, and from there, this is a tangent, this is a radius, so it's going to make it 90 degrees with this guy here. Do you agree that? Yeah, because we mentioned that. Great. Also, this radius, so that means that this guy here, remember this one here is to the end of the point of the contact, but that means, look at this, our triangle here. That means that this guy, if this guy is x, this guy too is also x. Great. And this guy is 90. That means this small parts here would be 90 minus x, right? So because the 13 is 90 degrees. Great. So 90 minus x. Let me make that clear. Now this is x. This is x. this angle is unknown, but we know that sum of angles in a triangle is equal to 180 degrees. So let me just say POQ plus x would equals 180. So angle POQ will be equal to 180 minus 2x, right? Or we could say 2 open brackets 90 minus x. Is that not it? So this angle here is 2 open brackets 90 minus x. Now if you look at this, this is the same image. This image here, this is one of the images that we had when we're talking about inscribed central angle theorem. So I'll just show it to you. Can you see it? Right, and we said if that is the case, the angle at the center inside the V would be twice the angle at the circumference. So if you take it back to what we have, that means that this angle here, so we know that from inscribed central angle theorem, angle POQ is equal to 2 times angle, this POQ is equal to angle PRQ. So angle PRQ will be equal to angle POQ divided by 2, right? So our angle POQ is this guy, so that will be 2 open brackets 90 minus x divided by 2, and if you divide both sides, so that your angle PRQ is 90 minus x. So PRQ, this inside here, is 90 minus x. And look at it, this guy here and this guy here, they're the same value. So this was, I think this was the alpha and this was the beta. So it's just showing that they are alternate angles, mean that they will be the same. Like, this is just a small proof to show that what we said there is correct. So I'll take it again. It says if a tangent is drawn to a circle and from the point of contact a chord is drawn, each angle which this chord makes with the tangent. Okay, so this is one chord, this chord 1, this is another chord 2. All right, you can see all coming from the point P. So this is each angle which this chord makes with the tangent, right? This guy here is equal to the angle in the alternate segment. So you can see this is segment 1. Let me just color it. This segment 1, right? This segment 2, right? Let me just try to do something like this. So each angle which this chord makes with the tangent, it makes this angle, is equal to the angle in the alternate segment. This is the alternate segment. So when you just see this, and when you see this image, just know that you're talking about alternate segment theorem, and you can prove it, which is very, very, very important. I want you to watch this video as many times as possible. Try the proofs by yourself. Refer to this video if you make any mistake, but please know them. If you check the WAEC syllabus, they are underlined, meaning that you need to know the proof. And if you have any question or suggestion, please drop it in the comment section. In the next video, we're talking about questions that cover, I think, all the theories, if I'm not exaggerating, all the terms that I've talked about. I'll see you guys there. Bye for now.